Hey everybody, just wanted to spend a little bit of time going over some of the more chemical concepts and some of the new vocabulary that we're going to learn with the ideal gas law. Let me get rid of the calculator. We're not going to need that for this. Okay, and so the first vocabulary that we want to introduce here is this guy, STP. That stands for Standard Temperature and Pressure. In order to do measurements, in order to make measurements, we needed something to be standardized. Because we know that as we change the temperature, the volume changes, and so we needed to come up with a standard temperature to measure all of these things, and not only a standard temperature, but a standard pressure as well, because we know that the pressure can affect all these things. So you'll see that as STP, okay, Standard Temperature and Pressure. And when you have a gas at standard temperature and pressure, we have something called the molar gaseous volume. That means 1 mole of gas has a volume of 22.4 liters for every 1 mole. And so that's assuming that we have 1 mole of gas, because it's in liters per 1 mole, and that whatever the gas is at standard temperature and pressure. So it's kind of like 3 standards here, okay? There's standard temperature and pressure, STP, and then there's this molar gaseous volume, which is a constant, which doesn't change, and that is this 22.4 number. Now, there are some assumptions that we make when dealing with ideal gases, and these are important. Okay, there's something called the kinetic molecular theory. We call it KMT. So it's kinetic molecular theory. And kinetic molecular theory of gases talks about all the things that we've kind of mentioned before, that molecules are small and they're in constant motion, and that motion exerts pressure in a container, all of those things that we kind of conceptually get. But we make 2 assumptions in order to make sure that gases are ideal. Okay? And those 2 assumptions are that molecules are very small. In fact, they're so small that we don't even consider them when considering the volume that they take, that the volume of the gas takes up. So in order for a gas to be as ideal as possible, they need to be as small as possible. And the other assumption is that there are no intermolecular forces. Now, I'm going to get rid of this, and I'm going to show you what we mean here by both of these. Okay, I'm going to draw a container. Okay, it's going to be, let's make it a balloon. Okay, it's got a little string. Okay, and so if I have a gas that's really small, that gas, as it's moving, occupies a certain amount of space, and it'll bang against the side and exert a certain amount of pressure because of its motion. Okay, temperature is a measure of its motion. And because it's small, we don't have to worry about it. Now let me take the same balloon, kind of weird here. Okay, and now let me make those molecules really big. Now, that's going to move around, but notice now that this molecule, if it's really big, takes up a lot of space in and of itself, and its motion, yes, is going to cause pressure, but it's a pressure of 2 large things hitting each other, not just the motion of a tiny little particle. So this big molecule may move just as much as the little tiny one, but its space that it takes up is going to be much bigger. So the assumption is that gases are small. In fact, that the molecules of gases are so small that they take up 0 space compared to the size of its container, and that's an important assumption. And the other assumption to make a gas ideal is that there are no intermolecular forces. So if we take this same balloon here, and again, ideal gas, let me redraw the top here, and we have molecules that are moving independent from each other, that means they can hit the sides of the container without being affected by anything. They're just moving independently. Didn't want to do that. Okay, but anyways, but if we have intermolecular forces in our balloon, what's happening is these molecules are going to be attracted to each other more than they're going to be hitting the wall independently of each other, and that's going to affect their motion. And so you're not going to see an exact temperature based on molecular motion. It's also going to be based on their forces. So these two assumptions are important to know. Now, let me show you a little sample problem here of what we're talking about. Okay, and it says, which of these gases deviates the most from being ideal? And I guess before we get started, I do want to say there is something called the Vander Waals equation. And the Vander Waals was Dutch, or Vander Waal was Dutch. That's why this is a V sounding, okay? And the Vander Waals equation takes into account all of these non-ideal conditions, and that's what we get if it's a non-ideal gas, okay? Now, we're not going to deal with non-ideal gases. The Vander Waals equation is really junky and hard to use sometimes. So we're just going to say, instead of saying use the Vander Waals equation to figure out what the pressure or the temperature is, what we're going to say is which of these deviates most from ideality, meaning when we do the ideal gas law, which one is going to be furthest off because of the assumptions that we make. Okay, and so we'll look at H2, F2, silicon tetrachloride, and sulfur tetrachloride. Okay, so now when we look at this, hydrogen is really tiny. Hydrogen gas, diatomic, it is tiny. It has a molar mass of 2 grams per mole. Okay, fluorine has a molar mass of 19 times 2 is 38 grams per mole. Okay, I guess I could do this using the calculator. I'll bring that up. So silicon has a mass of 28. Let me turn it on. 28 plus 35.45 times 4. So silicon, this has a molar mass of 169.8. And then sulfur has a mass of 173.8. So here's what I know. These two guys are not going to be the answer, because what do we need? We need them to be big and or polar. These guys are not big based on their molar mass. 2 and 38, not big at all. Okay, these folks are big, bigger at least. Okay, so now how do we tell the difference between these two and these two? We can't just say that it's this because it's bigger by 4. 4 is not a huge difference in size. What we can do is we can determine which one is polar. So if we draw the Lewis structure of silicon tetrachloride, and I'm leaving off the unshared pairs of electrons, I'll put them in there. Okay, chlorine has unshared pairs of electrons like this. Okay, what is that? That is a tetrahedral non-polar molecule. If we have sulfur tetrachloride, which again is roughly the same size, you'll note that the molecule here, in this case now, is seesaw. This is seesaw, my favorite one, seesaw. And what do we know about seesaw? Seesaw is polar, so there would be intermolecular forces. So this one would be the one that is the that deviates the most from ideality. So we would use PV equals nRT, but then say, well, that one's going to be the furthest from the actual answer. okay, the numeric answer that we get, because it is the one that deviates the most from ideality. So that explains a little bit about the theories behind the ideal gas law and how we can make those assumptions. And I hope you have a great day.